Liquid Ice.
Welcome to the first Liquid Ice seminar. We're EU-funded project with this lengthy title linking and quantifying the impacts of climate change on inland ice, snow cover, and permafrost on water resources and society in vulnerable regions. We're like big team. By big team, I mean consortium consists of 18 partners from Europe and India, major actors in cryospheric research in Europe and India, I would say. So the project is mostly about water resources coming from the cryosphere, meaning glaciers, snow, and permafrost in different scales, time scales, and spatial scales. So we got several objectives which are in situ data. So we plan to develop harmonized data sets for ice, snow, and permafrost. We also will push forward understanding of cryospheric interconnections and processes. Project also works with remote sensing, and in remote sensing we work with mostly with albedo products and snow water equivalent retrieval, hopefully. Then there's huge component focused on glacier and ice sheet mass balance reconstructions. We also work with Earth system models and downscaling of Cordex and RSM simulations. Then at the end, we'll provide integrated impact assessment on water resources, especially for 5 super sites. And super sites are Svalbard, where we'll work on impacts on environment. Then Greenland, where we'll focus mostly on water resources for hydropower. In Italy, we work with hydropower production and winter tourism. Then Himalaya, it's mostly freshwater production for over 1.5 billion people. And Norway, where we work with water for hydropowers, and that's where we come today with the seminar. Our speaker is Ekaterina Rets from Institute of Geophysics. She's an assistant professor. She's been studying how climate change affects the cryosphere for over 16 years. And how hydrological systems from glaciers and snow rivers are changing. She has experience in fieldwork in glacier regions around the world, including Svalbard, Caucasus, Tian Shan, Siberia, Altai, and Kamchatka. She developed a distributed energy balance model called AMELT, which is focused on alpine and ice melt. And she also co-developed the widely used R package called GRVAT. Katya is also contributing author to the IPCC 6 assessment report, and she's been recognized for her work in data science and hydrology. Then I will stop my lengthy introduction, and Katya, floor is yours.
Okay, so Bartek has introduced you to very briefly to the whole project, and I will be speaking generally about intermediate results from one of the tasks in this project. Declining cryosphere is one of the most evident and well-documented consequences of climate change. And though for snow cover, there's bigger disagreement and big uncertainties between different models and quite more considerable inter-data set variability than for glaciers, for example, but we're still quite confident in consistent negative winter and spring snow cover trends over the northern hemisphere. However, there's still limited knowledge how that translates to basin level changes in river runoff regime and hydrological responses to these changes. And even less is known about how that propagates and translates in societal impacts. And our project actually, like one of ambitions of our project is challenging this gap, going all the way from cryospheric changes to water depths. And we are on our way. And today I will be speaking only about one aspect that won't be strictly inside hydrological domain, because we will talk about how we characterize river hydrological changes, so that it can better help us attribute that to cryospheric changes and to produce more understandable, more practical conclusions for societal part. Regardless of what we are doing in hydrology, analyzing historical data or analyzing model outputs, hydrological model outputs for different periods, we're still dealing with a hydrograph, and we need to summarize and to convey the story of this hydrograph, like what is actually changing with the river, with its response. And those hydrological summary indexes that are mostly used for that, mean annual discharge, maximum minimum discharges, some low flow indexes, and monthly, also mean monthly distribution. But even from this quick glance from this picture, everyone can see that there's much more information in the hydrograph itself than in this monthly aggregation. So let's play a guess game. So what does this monthly distribution tells us about the hydrograph? What it would tell what a user about hydrograph? Let's look, for example, on the October. So what you can tell about October? Probably runoff was close to mean annual level. So something mild, something relatively okay. But what happened in reality? The first part of the month, there was quite deep low flow period, and probably water users, practitioners had to sustain the ecological flows during this period. And then we have a quite high intense flood and probably some water spill risks during this period. So, but on average, it was close to mean annual level. That means that like water practitioners, they don't live in the reality of these month bars. They live in the reality of events on the hydrograph, and it breaks between the events. So it would be like measuring mean body temperature in a hospital. So these patients are already dead cold, yes, and this one have high fever, but on average everyone is okay. So how we can find a better way to actually understand and convey the story of what hydrograph is telling us, and convey the story to water users, not to measure mean temperature in a hospital. So one of possible approaches is event-based approach to river hydrograph analysis. So what do we understand? How do we understand and define runoff event? So runoff event is these occasions when river runoff exceeds base flow. It has its start point, end point, and it has its major trigger. For example, it can be rainfall, or it can be snowmelt. Of course, it's not that simple. In real life, there are sometimes mixed triggers, but in most of the cases, we have one major, most important trigger for each event, and we can classify these events. If the events coincide, they can fuse in one huge runoff phase, and the most well-known runoff phase is spring snowmelt flood for those snowmelt-dominated regions. So now we are moving from standard hydrological summary metrics to genetically classified runoff events and phases and their metrics. So we don't measure mean body temperature in a hospital. We distinguish between patients with different diseases, with different problems, and we treat them separately and try to find a solution for each of them, generally speaking. Now, for that approach, we used the GRWAT R package that Bartek has already said I'm one of co-developers of. How does it work? It identifies each event on a hydrograph, its start and end point, then it separates base flow using different base flow indexes, then it classifies the event. First, it identifies spring snowmelt flood, that is a major phase or event during spring connected to snowmelt. Then it actually separates the year. It starts hydrological year from the beginning of the spring snowmelt flood. Why it is like that? Because recharge of groundwater during this phase, like this major phase, would actually define what happens with groundwater afterwards during winter. So separating it in January would not lead us to meaningful conclusions. That's why this approach is used here. Also, it identifies overlapping runoff floods on the spring snowmelt using precipitational criteria for precipitational criteria, and separates classifies separately rain floods and thaw floods, using also some criteria and indexes calculated from air temperature dynamics and precipitational dynamics. As input data, we used data from 55 gauging stations from the Norwegian stream flow reference dataset from 1916 to 2024. And for air temperature and precipitation, we used ERA 5 analysis. Actually, we have also some stations to proceed in the north. So for this whole presentation, you don't look much on the north because there will be only 3 gauging stations there. We analyzed around 3,500 river hydrographs, and there were different types of water regimes all across the territory. And this algorithm worked quite well for this A, B, D, and C, and for this F and E. There actually we needed a lot of manual checking and manual adjustment. So basically, we checked, we at least looked at all, had a glance at all of these 3,500 hydrographs to check if the algorithms works correctly and identifies events correctly. So first of all, let's look at changes in annual runoff. So here on the map, reddish colors on all of these maps would show increase in parameter, bluish colors would show decrease. And here you see that annual runoff during the last 2 decades have been higher by 15–30% in most of the territory, especially in the east, except for this middle part where annual runoff is declining. And I'm drawing your attention to this part because I will return to this region further in the presentation. And if all the available water resources could be used for hydropower production, that would be how our changes in hydropower potential would look like. But in fact, real hydropower potential would also depend on intra-annual distribution of this runoff, how these events and breaks between events would be distributed within the year. Norway, how the hydropower plants, they don't have too strict regulations, I would say, compared to other countries. They don't have legally fixed seasonal level curve, for example, only some boundary conditions and environmental constraints and obligations. But still, majority of Norwegian hydropower reservoirs were designed to capture runoff during this major spring snowmelt flood event. And during rain floods also, where they are present. And release the water during a winter period, and where there's high demand and low flood, they also need to have space to accommodate spring made flood for hydrological security. And there are also obligations to sustain low flow during to sustain ecological flow during low flow periods. So first, we'll be looking at this key phase in the hydrograph for hydropower production. So here's how spring snowmelt flood volume has changed during last 2 decades compared to historical period. I will refresh it that blue colors is a decrease and reddish colors an increase. And the size of this circle shows the relative importance of snowmelt flood in the total annual runoff. Should we actually care about this phase? Not, because, for example, for these coastal areas, it contributes around the mere 10%. So we shouldn't probably care too much what happens with spring snowmelt flood. Now, for the rest of the territory, we mostly see a quite substantial decrease in spring snowmelt flood volume, up to 15–30%, except for two regions, this one on the mountain range and the western slopes of this mountain range, and also one more cluster here. But if we look only on snow component, because this is full spring snowmelt flood volume together with overlapping rain floods and with underground waters. But if we look only on snowmelt component, then even this cluster sort of dissipates, and most of the picture is negative all over the territory. So what are the reasons and the physics behind that? So first of all of this spatial distribution it's in the good agreement to trends in snow cover that are observed around Norway. So that's a decrease in snow mass except for these mountain areas. And on top of that, so there are like two factors that are eating up this spring snowmelt flood. Is that warmer winters have resulted in more frequent and more intense winter thaws. So you see quite a dramatic increase in winter thaw runoff volume all over the territory, and it more than doubled for some of these territories, and duration is also increasing. As a result, like yes, from these two sides, spring snowmelt is drained and there is less snow, and snow is drained during winter. So we see a consistent decrease in relative importance of spring snowmelt all around the territory. And this decrease by 15–10% means that if, for example, in historical periods, spring snowmelt contributed 50% of the total runoff, after the beginning of 21st century, it would be like 35, 30%, 40%. So that is quite a huge difference. If we look at changes in relative importance of winter thaw, it's still not that much important, especially in the central areas, like except for coastal zones, but the importance is consistently rising. Also, the beginning of spring snowmelt flood is shifted to the early dates by 1–2 weeks in this southern part, first of all, and in the north. So how does it look in real life on a real life hydrograph? So that's example one river. So basically, we're moving from this kind of hydrographs to this kind of hydrographs. So with distinct spring snowmelt dominating and some small thaws, to low spring snowmelt flood and quite substantial winter thaws. Also, changes in regime of in winter regime, they also bring about changes in groundwater recharge, and the small wild winters they're beneficial for the groundwater recharge, and we see actually rise in annual groundwater runoff all over the territory. Here we logically can want to look at the low flow indexes, because it's also very important, because during low flow periods we need to sustain ecological runoff, quite important, and other ecological constraints. So as you would expect, during winter all the territory experiences rise in winter low flows. But for the summer, the picture is not that bright. There is some increase in the eastern part, but in the western, and especially here in the middle, it's most statistically significant. We see a quite significant drop in 30 days average minimum summer runoff. And here, of course, we should look at rainfall as well. So quite logically, rainfall runoff would contribute to this minimum 30-day summer runoff. And actually, it's in quite good agreement with this picture. So within these regions where we see the most evident increase in rainfall runoff, here we also see increase in minimum 30-day summer runoff. But once again, in this middle part that I've already stressed your attention to, we don't see compensating increase in rainfall runoff compensating this decrease in spring snowmelt. So here we also see a quite substantial decrease in summer low flow indexes. And once again, the annual runoff picture, so you see as well, yes, minimum. This middle part probably is one of problematic zones, because here we see both decrease in spring snowmelt and decrease in rainfall as well. So that is how relative significance of different sources looks all across this studied watersheds. It's sort of messy and not final picture, but so on the x-axis there are all of the stations, and here is the share of each component in a total runoff. Green one is rainflow, dark one is from the recent period, light how it used to be. Blue is spring snowmelt. Once again, dark one is last 2 decades, and blue one it's how it used to be, and brown one is winter thaw. Light one previous period, and dark one, the modern one. And just brief overview of the territory. So these are eastern regions, middle, west, glaciated rivers, and north. And let's look at some of these key zones. For example, eastern region. If previously spring snowmelt contributed almost 50%, like for 40 to 50% for most of the gauging stations, now it's decreasing to 20-30%. So, and on the contrast, rainfall runoff is compensating for that because of the increase in rainfall runoff, and its share is increasing up to 50-60%. Winter thaw is importance is also increasing, but not all of the snow that like used to be here is now drained in the winter, because part of this is gone because we have less snow mass, and part of it is recharging groundwater flow. So we won't see all of this in the surface flow. It's not just a simple redistribution from spring to winter. And also a brief look to this most critical area on the map, middle territories, where we have drop in spring snowmelt and no compensation in rainfall. And here winter thaw period becomes a really major phase of runoff regime. To summarize all these tendencies in one conceptual plot, blue line is historical period, orange one is modern period. So what do we see in the last 2 decades, and what tendencies are most likely to continue is lower and earlier spring flood, frequent thaws in the winter, higher winter low flow, increased rainfall in some of the territories, not everywhere, and decrease in summer low flow also in some of the territories. So what possible operational tensions that could result in is reduced spring refill availability, higher wind spill risks, and overall change in flood control constraints, and challenges to sustain ecological runoff in summer as well. So this is this was a sort of analysis of potential pain points, both in seasonal and both on the map, and forming hypotheses that we want now to change to check in the future how modern operational strategies, how they will work on this changed conditions that would most likely deteriorate in the future, looking at the trends and projections in snow cover and air temperatures. So how we are planning to test this hypothesis is we're planning to use outputs from Earth system models and hydrological models within the project that are going to be run, choose storylines using the structural analysis, identifying pain points and hypotheses, and feed these outputs to hydropower response model. This is, we're still deciding how, in what way we will do this. Probably it will be some simplified conceptual approaches, but we also wanted to test machine learning-based hydropower plant operational models, but that would require quite a lot of data from the hydropower plants, of course, and would be feasible only if we could find some industrial partners that would be willing to cooperate over that. And so we will be testing how operational strategies that are now used, how they will work in this future climates with these challenges that we already sort of outlined, and what adaptational strategies and where in what of the territories would be most likely needed in the future. And I will leave this slide as a final one with this future plans and requests to the community, and also my contacts there in case you're interested and want to contribute. Yes, and I would be happy to answer any questions if there are any.
Yeah, thank you, Katja. And I think we may start the discussion. So if there are any questions, please either unmute your microphone or write on chat. And yeah, I think we have a comment from Jan, very minor correction, AVI ESM3 instead of AVI ESM2. But it's technical correction.
ESM3. Yeah, it's a big correction. I'm sorry, like that's sort of a typo, because like we are on moving on in this direction. Yeah, thank you for the correction. That was a fast slide, like this last one. Don't judge it too much. Yeah, Olga.
We have a question from Olga.
Yeah, Olga, University of Oslo. I have actually two comments, I think. One comment is that I wouldn't use 1961 to 1960 to 1981 data, discharge data, for such kind of analysis, because we generally consider it not that good quality compared to all that comes after 1981. That's just one comment. And then I'm curious if it was error 5, was it bias corrected precipitation? Or
Yeah, about error 5, and I also have some hidden slides for that, because actually this yeah, thank you for first of all about the comment of hydrological data sets. Yes, actually some of the rows they start from 80s, some of the rows start from 60s, and I've checked whether tendencies depend on like what period we choose, but I would say basically there is not much changes in tendencies. There are of course like changes in absolute values, like 15 or 11%, like something like that, but the tendencies remain the same. But probably as we should do it more consistent and start everything from 80s. And about era 5, the comment is that what we are using is strictly not a hydrological model, but a classification algorithm. So actually, precipitation and temperature they are used as sort of threshold sums, and it's not very sensitive to the absolute values. For example, like that is example from some hydrograph. So that is precipitation sum of 50 millimeters during, I don't remember how many days, because it's also collaborative parameter. So it's like if it's 50, then we have very long spring snowmelt flood. If it's 40, then it identifies this one as already rainfall contribution. And if it's 30, it also identifies this peak as rainfall, but in fact, most likely it's due to snowmelt. So that's, for example, I would use this one as a measure. So it doesn't use precipitation temperature to recalculate it to hydrological time series. It just uses some threshold values to classify. So so that's why we use, for example, error 5, not error length or anything more precise, because it's not very sensitive to these two values. It doesn't care much if it's like, I don't know, 15%. You can change all the data by 50% and you will get the same hydrograph.
I see. Thank you.
Yeah, Baptiste, please go on.
Yeah, thanks, Katja, for a nice presentation. Actually, my question is related to the one from Olga. So you don't expect any change in the hydrograph separation from biases in ERA 5. I was thinking about other reanalysis like CARA 2 that is now resolving the topography at a higher resolution. Do you think it's also going to be resistant to, or like the results will be the same with something higher resolution like Cara-2?
Yeah, that generally the short question would be yes. The long answer is actually I was planning to use Cara when I started this work, but the Cara-2 wasn't yet released when this work started, and it didn't cover all the territory. So that's why we actually went with ERA 5. And if we go to this input data, I would show you. Actually, it's even integrated data for the whole points that cover the watershed. So, and actually increase in accuracy of rainfall and temperature data wouldn't change much the classification here, because it first of all it uses the time series itself, and then it only like classifies the events if it's due to snowmelt or if it's due to rain, and you don't need very precise data for this kind of because half of the answer is in the hydrograph itself, and then in this threshold criteria. And also we want it to be quite stable for the whole period and for the whole territory, so that we can. But I basically use almost the same parameters for the whole Norway territory, I would say. Like not that would be too much for the whole, but for large clusters I use the same set of parameters, and it works well like in large clusters because it's not a model, it's a classification. But you would need different classification parameters for basically like these 6 types. You would need different set of classification parameters, but inside this type you would use the same classification parameters. So I don't expect increase in accuracy using more accurate data. I would expect increase in accuracy. I have some ideas how to improve this classification, and I'm thinking of adding very simple snowmelt model to that to increase accuracy. I think that would actually make a huge change.
Yeah, thanks.
Rose? Go on, Rose.
Katja, in your last answer, you said something very interesting. You described the separation as working well. Can you say a little bit about how you decide when it's working well and when it's not working well? What are the diagnostics that you use?
Yeah, that's actually not that easy question, because the best way to decide if it works well or if it doesn't work well would be using isotopic, for example, hydrogas separations. Of course, I wouldn't find this kind of data for this kind of period, for this kind of territory like Norway. But in some previous experiments with this algorithm, we've checked how it works on those rivers where this data is available for quite long periods, like several years, for example. So I would say it's somewhere in between this experience of using it coupled with isotopes and experience of analyzing and modeling river hydrographs. So that would be my evaluation would be expert one, and the best way would be to bring to really check it. It would be to bring, for example, 5 experts in hydrology, show them some random hydrographs from a separation, and ask their opinion on the quality. That I think that would be, and use isotopes when they're available. Of course, that isn't possible for this kind of huge territories. So so yes, that would be the answer.
Okay, thank you very much. Yeah, for me, this is a super interesting application of expert knowledge and experience, because you can see things with your eyes. And
yeah,
this is super interesting that this plays a useful role.
Yeah, the next thing, actually, what I was thinking about, my future idea is to use this expertise, like invite 5 expertise and show some random hydrographs for them. You know, this ChatGPT style, and like click on one that you like more, you think right, and then feed this all to large language model, and then like try to sort of formalize this expert approach using large language models. I think it would be like one of the best ways to proceed further with this kind of classificational approaches.
Maybe that would be a good exercise for the next General Assembly with many experts in that.
Yeah, actually, we can do like some sort of like quiz over a beer. Yes, to choose a hydrograph you like better, this one or this one, how it's classified, from opinion, and then like, it's a nice
human machine learning.
Yeah, but like the machine learning is based on it's more or less based on the human virological networks. They try to reproduce it anyway. So basically, yes, that would be close.
We still have like a few minutes for any other questions. We may wait a little bit.
I'll return
or
to this, my last slide that I'm on. Yeah, I see a comment
Ross
from
would like to comment again or ask a question.
Yeah, I have a different question. So when you made your sum, maybe just leave it with one of these maps of Norway. And one of the things you identified several times was different geographical clusters. So different parts of Norway that have different behaviors. Is this because they've experienced different climate shifts in different places? Or is it because they've experienced kind of the same, for example, the same warming, but they're in different regimes somehow, that maybe colder places and warmer places respond differently when you warm them by the same amount? So is there different climate change in different parts of Norway in the past?
Yeah, that's very interesting question, and that is also what I'm thinking about. And there is also like a field for the further analysis as well, because this analysis is not finished for sure. But I've tried to compare those trends with those trends that have been observed in temperature and in snowfall, at least. And also, of course, with distribution of glaciers and with the distribution of elevations between these watersheds. And there are quite consistent tendencies. For example, like I've shown a comparison between these tendencies in spring snowmelt flood and changes in snow water equivalent. So you see this cluster with where amount of snow has increased. It sort of coincides with this region where we have at least less decrease in spring snowmelt flood. And also here we have some glaciated parts, and there you see this red dots from where you have mobilization of meltwater resources from warming. And also there, actually Norway is pretty interesting from hydrological point of view, because there were very contrast conditions on very small territory. In the coastal zones, you see quite a lot of increase and in winter thaws, and quite high importance of this winter thaws. So and so these changes in winter thaws would contribute to changes already in annual runoff, though in some inner territories it's not. So like actually there is you can write a book, I think, about how as Ross said, how these initial conditions of watershed, their geographical position, their conditions, placement in the elevation, distance from the shore, and exposition of the slope, western one or eastern one, how it actually transforms this cryospheric signal into runoff response that would be quite more contrast than initial temperature and cryosphere signal. So yeah, so we have after translating this signal through river hydrographs, we have next level of complexity of the picture compared to which one we get from temperature and snow itself. Yeah, I guess it answers Ross' question a bit. Yeah, thank you for these interesting questions. Very nice discussion, and thanks from also the expertise from those who are experienced in this in Norway conditions, because that is something I'm really lacking, and I'm really looking forward to contacting with those people who are actually experienced in working with hydropower industries here in Norway in the fields, because I'd really appreciate insights from that side, because you need actually to know quite a lot from how things are done locally to understand things sometimes.
We have one more question from Jan.
Yeah, thank you very much for this nice talk. I was wondering if this would be an interesting use case for things like destiny or this kind of high resolution projections where you get quite a bit more of the orographic intricacies of Norway compared to ERA 5 or other models, because those runs I think have been done at 9-kilometer atmosphere resolution, some of them 4.5. So, and I know that there are some hydrographic users already downstream of those simulations. And it's not always the easiest data to work with because they're very large, but it seems to me like this would be an interesting application for this data.
Yeah, I think what you're talking about, it would be very useful for this second part of our plans, like future plans. This one. Yeah, am I still no, I'm not sharing. So like for our, yeah, I'm not sharing, but like I'll tell it in the words. For our future plans, when we are willing to do some study cases for the smaller territories to check the operations and what's going on for some certain places. So there, this high resolution data sets for sure would be defining to realistically reproduce what is going on right now and to check what will happen in the future. So thank you for it here. Yeah.
So thank you very much, Katja. And a short announcement, not exact, not precise yet. However, we are thinking about the second LIQUIDICE webinar to be dedicated to some social aspects of conducting research in the Arctic. And it will be presented by Lille and maybe Asta or in collaboration. And we will announce it somewhere at the beginning of autumn. So it will be probably in early October. So thank you very much for today and stay tuned for next meetings.
Thank you, everyone. See you.